This paper is from 1991, 4 experts. The entire input is 2 numbers. This one is from last month. 2.8 trillion parameters, 896 experts. Same diagram, same gating equation. One author on both. The second one uses the first one's idea for a reason the first one never mentions. Not once. In 9 pages. I'd read both of these papers. I never noticed. Mixture of experts is the architecture behind basically every frontier model right now. It was invented 35 years ago to solve a problem we no longer have. This is the story of an idea that changed jobs. 1991. Adaptive mixtures of local experts. Robert Jacobs, Michael Jordan, Stephen Nowlan, Jeffrey Hinton. Neural Computation, Volume 3, 9 pages. If you train one network with backpropagation to do different subtasks on different occasions, you get, quote, strong interference effects that lead to slow learning and poor generalization. One set of weights, 2 jobs. Every gradient step for job A partially undoes job B. The network isn't learning 2 things. It's negotiating a truce between them. Anyone who has managed 2 stakeholders with opposite goals already understands this architecture completely. So their fix? Stop using one network. Use several expert networks, plus a small gating network that decides which expert should handle each training case. Now, when an expert gets a case wrong, the weight changes are localized to that expert. Nothing else moves. The experts are decoupled. The gate is a softmax over the experts. Then they had to prove it worked. The task was telling 4 vowel sounds apart, from 75 speakers, men, women, and children, recorded for an acoustic study in 1952. The input to the model was the first and second formants, 2 frequency values, 2 numbers in, 4 classes out, 50 speakers to train on, 25 to test on. Each expert was deliberately crippled, restricted so it could only draw a straight line. That is the founding experiment of the architecture that now runs on tens of thousands of accelerators. 4 systems, 4 experts, 8 experts, and 2 ordinary networks sized to have about the same number of parameters. Accuracy on the training set, 88%, 88, 88, 88. On the test set, 90, 90, 90, 90. The mixture of experts was not more accurate, at all, in any configuration. What changed was the last column, epochs to converge. The ordinary networks needed about 2,200 and 2,400 passes through the data. The mixtures needed about 1,100, half the epochs for identical accuracy. That was the result. That was the whole paper. That same column has one more thing in it. Going from 6 hidden units to 12 made the ordinary network worse. 2,200 epochs to 2,400. Going from 4 experts to 8 made the mixture better. That's a scaling result. In 1991, at a scale of 8. They ran each system 25 times. In every one, with 4 experts, or with 8, all but 2 or 3 of the experts ended up with a mixing proportion of effectively 0 for every single case. With 8 experts, 5 or 6 of them did nothing at all. The paper never treats this as a problem. It comes up in a figure caption, in passing. Quote, the system tends to use as few experts as it can to solve a problem. It's presented as a virtue. Parsimony. The model worked out it only needed 3, so it used 3. Modern papers have a name for that behavior. They call it routing collapse. The experts start identical. The gate gives everyone equal weight, so every expert drifts toward the same compromise solution. Then the symmetry breaks. One expert happens to do slightly better on one pair of vowels, gets more responsibility for them, gets better at them. It ends with expert 5 separating one pair of vowels and experts 4 and 6 separating the other. You can point at each expert and say what it does, in plain language. That was the headline claim of the paper. The learning procedure divides the task into appropriate subtasks. That one doesn't last either. 1994. Jordan and Jacobs generalize it into a tree of gates and fit it with the EM algorithm. That moves the idea out of neural networks and into statistics, and then it just works, quietly, for 20 years. In 2012, 3 researchers published a survey called 20 Years of Mixture of Experts. It's a good survey. It's thorough. Here's what mixture of experts had been used for by 2012 in their own list. Predicting electricity demand, climate prediction, reading handwriting, robot navigation, face recognition, classifying EEG signals, classifying heartbeats, classifying stars, protein interaction prediction, analyzing voting behavior in elections, predicting the dollar-to-pound exchange rate, and landmine detection. Not one of those is making a model that's too expensive to run, runnable. I searched the whole survey. The phrase computational complexity shows up only as a problem, the cost of fitting the thing, never as the reason to use it. The conclusion recommends mixture of experts for, I promise this is real, small training sets, where it generalizes better than a plain network on a vowel task. 21 years in, the field's own summary of the idea's best use case was still the experiment from the original paper. Its future direction section bets on time series classification and, again, landmines. 5 years later, the answer was language models. Nobody saw it. Not because they weren't paying attention. These are the people who knew this literature better than anyone alive. They just didn't have the problem yet. 2017, outrageously large neural networks. 7 authors: Noam Shazir, Azalia Mirhosseini, Christophe Maziars, Andy Davis, Kwok Lee, Jeffrey Hinton, Jeff Dean. Same Hinton, 26 years later. The first sentence of the abstract. Quote, the capacity of a neural network to absorb information is limited by its number of parameters. Nothing from 1991 is in that sentence. Interference, gone. Crosstalk, gone. Slow learning, gone. Generalization, gone. The problem is now that you want more parameters than you can afford to compute with. That's a different complaint. It's not about learning anymore. It's about a budget. The fix they reach for is the 1991 architecture, unmodified in its essentials, cited in a single sentence as prior art. But they do change 2 things. 1, only run some of them. The gate picks the top few experts, and the rest are never evaluated at all. In 1991, every expert ran on every input, and the output was a weighted average of all of them. So the original mixture of experts saved you nothing at runtime. Not a single operation. It was never trying to. Top K routing is what turns it into an architecture whose entire value is what it doesn't compute, and that is the one part that isn't in the original paper. 2, make the number enormous. Their largest configuration has 131,000 experts and 137 billion parameters in a single layer. In 2017, bolted onto an LSTM, before anyone had trained a transformer worth talking about. Then a third thing happens. They didn't design this one. They report a failure mode. Quote, the gating network tends to converge to a state where it always produces large weights for the same few experts. And this imbalance is self-reinforcing. The favored experts get trained more, so they get picked more, so they get trained more. That is the exact behavior the 1991 paper described as using as few experts as it can. Same phenomenon. Opposite sign. In 1991, it's parsimony. In 2017, it's a bug with 2 dedicated loss functions pointed at it. The reason it became a bug isn't about learning at all. At this scale, the experts don't fit on one chip. They're spread across many. So an expert nobody routes to isn't elegant restraint. It's an accelerator you are renting that is doing nothing. The 1991 paper let experts die because the task only needed 3. Modern systems forbid it because the hardware needs all of them busy. After that, it's an escalation. 2020, G-shard. 600 billion parameters, 2,048 experts, translating 100 languages. 2021, switch transformer, 1.6 trillion parameters, and they cut routing down to a single expert per token because it turned out 2 wasn't necessary. Switch also gives us the load balancing loss in the form everyone still uses. It's minimized, they write, under a uniform distribution. So, a term in the objective function whose optimum is every expert being used exactly equally, which is a penalty on the outcome the 1991 paper was built to produce. There's also expert capacity. Each expert gets a fixed size slot. If too many tokens want the same expert, the overflow doesn't get a second choice. It skips the layer completely. In 1991, the entire idea was routing each case to the expert that handles it best. Now, if too many cases agree about which expert they want, we throw some of them away, because the buffer is a fixed size, because it lives on a device. Then 2024. DeepSeek v3, 671 billion parameters total, 37 billion active per token, 256 routed experts, 8 of them awake at a time. And last month, Kimi K3, 2.8 trillion parameters, 16 experts active out of 896. About 96% of that model is asleep for any given token. That is not a side effect. That is the product. In 1991, you could point at an expert and say that 1 separates these two vowels. Can you still do that? People have checked this carefully more than once. Partly yes. In 2022, the ST mixture of experts paper went looking, and in the encoder it found real specialists. A punctuation expert, a conjunctions and articles expert, the, a, and. A verb expert, a proper names expert, a numbers expert. Which is real specialization. It's just not what anyone pictures when they hear the word expert. Then the same paper looks at the decoder and reports that it does not observe meaningful specialization there. Not semantic, not syntactic. Every model I've named in this video is decoder only. Mixtral 2024 checked again on a shipping model. Their word for the result was surprisingly. They ran maths papers, medical abstracts, and philosophy through it, and the distribution over experts came out nearly identical. No topic structure. What they did find was syntax and position. The same token tends to go to the same expert, and consecutive tokens tend to stay with the expert before them. So there is no maths expert. There is no code expert. There is no French expert. The router is mostly reacting to what the token is, not what the text is about. And the field noticed. There's a 2024 paper from DeepSeek whose title is Straight-Faced Towards Ultimate Expert Specialization. Its argument is that you have to engineer specialization back in. Slice the experts finer and hold some aside as shared ones to absorb the generic work. That's a paper about getting back the property the 1991 model produced by accident on a val task, with 4 experts and 2 input numbers. What survived, unchanged, for 35 years, the gate is a softmax over the experts. The output is a weighted sum, the diagram is the same diagram, and the word expert. What didn't survive? The reason. Interference between subtasks isn't why anyone reaches for this anymore. Nobody measures mixture of experts and epochs to converge anymore. The original ran every expert on every input. Nothing does that now. Unused experts went from a feature to a bug with its own loss function. And the legible, task-shaped specialization, the headline result of the original paper, did not survive contact with scale. The mathematics is nearly untouched. The justification has been completely replaced. It's the same building. Every tenant is different. I don't think the lesson here is read old papers. Everyone says that, and nobody does it. The lesson is more specific than that, and more useful. The reason an idea is good is not fixed. 4 people solved a small learning problem in 1991 with 4 experts and a 2-dimensional input, and were right about it for reasons that turned out to be almost irrelevant. The thing they built was the answer to a hardware problem that would not exist for another 26 years. Nobody connected the two until the problem actually showed up. Not them, not the survey written 21 years in. Which means the useful question isn't what's new. It's what's sitting in a 1990s journal right now, solving a problem nobody has, waiting for the thing it's actually for to break. Papers are linked below. The 1991 one is 9 pages, and you can read it tonight. If this was worth your time, a subscribe genuinely helps. And tell me in the comments which idea to trace back next. That's usually what decides the next one.